Every monsoon season, India loses more than 20% of its rural roads to water. The subgrade turns soft, the base layers wash away, and what took months to build becomes a line of potholes and broken asphalt in a matter of weeks. The solution engineers eventually arrived at was not a new synthetic material or an imported technology. It was sitting in a pile of agricultural waste behind every coconut processing facility in Kerala. This is the story of how India figured out that the husk of a coconut could hold a road together through a monsoon better than many materials designed specifically to do that job. The problem is not rainfall alone. In southern India, monsoon seasons arrive twice a year and can drop hundreds of millimeters of rain in a matter of days. That water moves through the road surface and reaches the subgrade beneath. It saturates the soil and turns compacted ground into something closer to mud. Once the subgrade loses its bearing capacity, every vehicle that passes over it pushes the road layers deeper and shifts them sideways. The surface cracks from below. The cracks open. Water enters faster. The damage accelerates. Entire road sections sink unevenly, becoming impassable for the trucks and ambulances that rural communities depend on most. What engineers needed was a layer that could hold the boundary between the subgrade and the road base in place when water was moving through both, permeable enough to let water pass, but strong enough to prevent the two layers from mixing and sinking. Coconut husk fiber, known as coir, has a property that almost no other natural fiber shares at scale. It is exceptionally high in lignin, the same polymer that gives wood its structural rigidity and resistance to decay. In most plant fibers, lignin content runs between 20 and 30%. In coir, it exceeds 45%. That high lignin content keeps the fiber from breaking down in wet soil and maintains its stiffness under load, so the woven mesh holds its shape when gravel and asphalt are placed above it. Studies on coir geotextile installations found that the fabric sustains effective soil reinforcement for 3 to 5 years underground before beginning to biodegrade, and as it decomposes, it releases organic matter that improves the subgrade structure over time. The fiber needs to last long enough for the compacted base above it to become self-sustaining, and it does. India has no shortage of this material. Kerala alone produces roughly 66% of the world's total coir fiber supply. Southern India harvests more than 19 billion coconuts every year, and until the geotextile market developed, the majority of those husks were agricultural waste with limited commercial value. The same regions producing the most coconuts were the same regions where waterlogged subgrades were making roads impossible to maintain. That alignment made the engineering case straightforward. In 2020, India's Ministry of Rural Development formally approved coir geotextiles under the National Rural Roads Programme, known as PMGSY3. Everything begins in the coconut groves. Workers climb palms that can reach 10 meters, cutting clusters of mature coconuts and letting them fall to the ground. The husks are stripped from the shells using a sharp metal spike, and a skilled worker can process between 500 and 1,000 coconuts in a single day. The fibrous husk makes up between 35% and 45% of the coconut's total weight. That husk, which would otherwise be composted or discarded, is the raw material for everything that follows. The stripped husks go through a process called retting, soaked in water for several weeks to loosen the bond between the long structural fibers and the surrounding pith. Without retting, the fibers cannot be cleanly separated during mechanical processing. After retting, the husks are dried under natural sunlight for 2 to 4 weeks, reducing moisture from around 65% down to roughly 15%. Once dry, the husks are fed into a decorticator, a high-speed separation machine whose rotating blades and tearing rollers release the long coir fibers and remove the inner pith. The fibers pass through a rotary drum sieve, leaving only the clean, long strands needed for weaving. A final drying stage over 3 to 7 days brings moisture below 5%. At that level, the fiber is stable and ready for spinning. Spinning machines twist the long coir strands into consistent yarn bundles. A typical facility processes around 3 tons of fiber per day. The fibers are sorted by length and twisted to a specified density. Uneven twist creates stress points in the finished geotextile that fail under repeated vehicle weight or sustained water pressure. Every spool is checked before it reaches the loom. In the weaving section, bundles are wound onto spools and fed into industrial looms. Longitudinal strands form the structural backbone of the sheet. Cross strands are woven through at right angles, creating an interlocking mesh. The mesh must be open enough to let water drain freely and tight enough to prevent soil particles from passing upward under water pressure. The loom moves in a continuous rhythm, and the finished fabric rolls off with a coarse, natural texture and measurable tensile strength that meets construction standards. Each roll is inspected before being coiled for transport. On site, the soil subgrade is graded and compacted to establish a firm level base. The coir geotextile rolls are pulled forward along the road alignment and unrolled along the full road width. Edges are secured using steel stakes. Where 2 rolls meet, they are overlapped by at least 30 centimeters. A gravel subbase is spread on top and compacted, locking the fabric in place. The coir layer distributes load from above across a wider area of subgrade, reducing the point pressure that causes soft soils to deform. A final layer of crushed stone is compacted before asphalt is applied in standard passes. The finished road looks identical to a conventional rural road. What is different is what happens during the next monsoon. The coir layer prevents the subgrade and the base from mixing under water pressure. The base stays clean, the subgrade stays intact, the road stays on the ground. India's Ministry of Rural Development mandated this approach under PMGS 3 in 2020, requiring 5% of all new rural roads in the program to use coir geotextile technology. That translated to roughly 1,600 kilometers across 7 states: Andhra Pradesh, Gujarat, Kerala, Maharashtra, Odisha, Tamil Nadu, and Telangana. The budget allocated for the geotextile requirement was 70 crore rupees, roughly $10 million. By mid-2021, nearly 100 kilometers had been completed, and national quality monitors found those roads were performing well. Studies found coir geotextile installations reduce soil erosion by around 50% compared to conventional subgrades and can cut maintenance costs by roughly 30% over the road's usable life. In regions where coir is locally available, the geotextile layer is also cheaper than synthetic alternatives because the raw material and processing infrastructure already exist nearby. The approach has real constraints at scale. The fabric degrades over 3 to 5 years, which is intentional, but the road must reach full structural stability within that window. In extremely waterlogged sites or where soils are highly expansive, coir alone may be insufficient without additional drainage engineering. The program targets 7 states where coir supply is concentrated, and extending it to northern states where coir is not locally produced raises costs significantly. What the program has already demonstrated is straightforward. The connection between an agricultural surplus and an infrastructure problem was real. Engineering that connection correctly was achievable at reasonable cost. The husks that were composted or burned behind processing plants in Kerala are now laid under road surfaces that survive conditions that used to guarantee failure. The fiber does not last forever underground. It does not need to. It lasts long enough for the road above it to become something the monsoon cannot undo in a week. Whether that performance holds as the program scales, and whether the supply chain can grow without eroding the cost advantage that made it viable, is the question the next several years of construction data will answer.